So, in the last class, we had discussed what are combinational circuits, how are they different from the sequential circuits, and we had seen how to design any particular combinational circuit that is given to us, the problem statement of which is given to us. And then we had proceeded to look at what is a half adder, and we had defined what it does, and then we had seen how to design the half adder. Is that clear, students?
Yes, ma'am.
Is there any problem?
No, ma'am.
Right. Okay. So today we are going to head on to designing the full adder first, and then we'll turn our attention to the subtractors, wherein we will discuss the half subtractor first and then the full subtractor. Okay, so we're going to be looking at the design of these three circuits today. I'm presenting my screen. Please let me know once you can see it. Is it
Ma'am,
visible?
yes, ma'am, it's visible.
Yes.
Right,
Yes.
thank you. Okay, so we are going to start with the full adder. What is a full adder? Full adder is again an electronic circuit which falls in the category of adders. It is responsible for adding 3 bits of information. Okay, we can add 3 bits together using a full adder. Okay, now see, half adder is not a sufficient adder in itself. Okay, why? Because since it can add only 2 bits at any given instant of time, and whenever we are adding 2 bits, even if we are adding 2 bits, we can get a carry out of this. Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
If we get a carry towards the next position, the half adder will not be able to handle that. Okay, because then at the next significant position, that is at the next bit level, what it will have to add is the 2 bits, namely the organ and the addend, and the third bit, the carry bit, which it will not be able to handle. So even for the most simplistic additions, full adder is generally what is required. Is this clear to everybody?
Yes, ma'am. Yes, ma'am.
Okay. Yeah. So who is going to some new child who'll read to me today from
Ma'am,
the
Asta?
screen? Asta.
Yes,
Yes.
ma'am.
Yes, please, Asta.
We saw in the section 1.4.1 that a half adder is capable of adding 2 bytes of information. However, when we add two binary numbers, a carry from previous significant bit is also required to be added along with augment and addend. The necessities the design of a circuit that can add three
This
bits of
necessitates
this
that
necessity This necessitates the design of a circuit that can add 3 bits of information at a given instant of time. Such a circuit is called a full adder.
yeah. Yeah, read on.
Thus, the objective of a full adder is to generate the sum and carry of 3 bits, namely the augment, addend, and the previous carry, that is, carry from the lower significant bit. Figure 1.4.21 gives the block diagram of a full adder.
So now please see, in this one line, that I have written, that is the objective of a full adder is to generate sum and carry of 3 bits. Okay, so in this line, we have actually set the stage for drawing the block diagram, which is the first stage of the design of a combinational circuit. Yes, because please see, I should be able to identify what are the outputs required. Okay, they will be, because it is adder, again, they will be sum and carry only, right? And in this case, there are going to be how many inputs? There are going to be 3 inputs, that is the augment, addend, and the carry. The carry from the lower significant bit. Any problem?
No, ma'am.
No, ma'am.
Accordingly, we can draw the block diagram of the full adder. Okay, so you can see here the full adder, the 3 inputs, organ, addend, and carry in, represented by X, Y, and Z, and the 2 outputs, namely sum and the carry out, represented by S and C literals, respectively. Any problem? Any
No, ma'am.
problems? Right. What is the next step?
Draw
What is the
a
next
truth
step for
table.
designing a
Truth table.
combination
Draw a
circuit?
truth table.
Truth table.
It is to draw a truth table, right? Yes. Astha.
Okay, ma'am. The truth table of a full adder can be drawn corresponding to the combination of the three input variables augment, addend, and the previous carry x, y, and z respectively, and the corresponding outputs sum and carry s and c respectively, as
And
illustrated by
yeah,
table 1.4.2.1.
yeah. So this is the truth table for a full adder. Let us look at it in detail now. Okay. So please see, when I'm adding 0 or 0 or 0, what will I get? 0 plus 0 is 0 plus 0 is again 0. So both sum is 0 and the carry is also
0.
right.
0.
Let us look at the next input combination. So here 0 plus 0 plus 1 is 1, sum is 1, and the carry is
0.
right.
0.
Next case is the same, 0 plus 1 plus 0 again generates a sum of 0 and no carry, right? Let us look at the next case. So here 0 plus 1 is 1 and 1 plus 1 is
1 0.
0.
2, which is the binary, which is the decimal equivalent of 1 0.
2.
So as we had done in the half adder, the sum gets 0 and the carry out is 1. Okay, so carry in is, this is the previous carry is also sometimes known as a carry in, because it is coming from, it is coming to get added along with the organ and the addend from the least significant bit. Okay, this carry is sometimes also known as a carry out. Why? Because this is the carry that is being generated out of the sum that has been produced by the adder. Okay, so as was the case in the half adder for this tuple, if you remember, this is the same tuple almost. So the sum is 0 and the 1 is carried forward to the next significant bit. Is there any problem up till now?
No, ma'am.
Right.
No, ma'am.
So again in the next combination, there is a single one, 1, 0, 0. There is a single one, which will get us a sum of 1 and a carry of 0. Any problem?
No,
No,
ma'am.
ma'am.
No,
Right.
ma'am.
Excuse me, ma'am. Ma'am, 1 plus 1 in sum is 0 and in carry is 1. How that's possible?
Come again, please. Who is this?
Ma'am,
What's
Ria.
your name, Beta?
Ria,
Anji?
Ria. Ma'am,
Ria,
why?
you are the new student, if I
Yes,
if
ma'am.
I'm not mistaken. You did
Yes,
not
ma'am.
attend the last class?
No, ma'am.
Right. Okay. So no problem. I'll tell you, but after this class, I'll send you the recording, okay, of the previous lecture as well as for this lecture. So you can go through that. And who else
Okay,
has
ma'am.
joined? Two people have joined or more?
Yes, ma'am. I'm also joined.
What's your name?
Ma'am, Shweta
Shweta
Chaudhary.
Chaudhary.
Yes,
Shweta
ma'am.
Chaudhary.
Yes, ma'am.
Right. Okay. Yeah. So I request you to please send me the request for access of the lectures. Okay. I think Shweta, you've sent me. I
Yes,
just saw
ma'am.
your message. Yeah. So everything is accessible. You both of you have joined the classroom.
Yes, ma'am.
Yes,
And what about the WhatsApp group?
Join, ma'am.
yes, ma'am. Joined.
Okay. So all the lectures are available on the classroom. Okay. But to access them, you will, all the links are there. But to access them, you need to send me a request for each of them. Just send me a request for each of them, and I'll add your mail ID to the shared people's list. Okay. So send me a WhatsApp, send me a text with your mail ID so that I can add you. Okay.
Okay,
Both
ma'am.
of
I
you.
have sent you.
You have
I
sent
sent
me for
you.
two
Yes,
lectures,
ma'am.
I think, or one
Yes,
lecture, I
ma'am.
don't
Yes,
know.
ma'am. Yes, ma'am. For two lectures.
So send it for all the lectures, okay? And then I'll
Okay, ma'am.
add in people, right? So you will be able to uh, attend almost, virtually attend all the classes. You will
Okay,
not
ma'am.
miss out on anything. And so this will be your assignment now, both Ria and Shweta Chaudhary. I want you to go through all the lectures,
Okay,
specifically
ma'am.
the chapters that we are doing, or the first you do the topics that we are doing, so that you're able to understand what we are doing in the class, right?
Okay, ma'am.
Okay, ma'am.
Yeah, so I'll just show you. So this is the case, please see. So here we're doing 1 plus 1, right? Now, how is 1 plus 1? What is 1 plus 1 equal to? If I do it in decimal number system, that means a normal maths, it is 2, right? But in binary, we write 2 as 1 0. Okay, in binary we write 2 as 1 0, and therefore 0 remains at my sum position, and 1 is carried forward as a carry to the next position. Is this clear?
Yes, ma'am.
Okay, you see the recordings, previous recordings, it will become all the more clearer, right? Yeah. Let us look at the next case now, 101. So again, two ones, the sum is 0 and the carry is 1, as we have just discussed. The next case is 6, that is 110. Again, the same case, that is the sum is 0 and the carry is 1 because there are two ones. Now let's look at the last case. So there are three ones here. So what do I get? 1 plus 1 plus 1 is equal to 3, right? Is that right?
Yes, ma'am.
Yes,
Right.
ma'am.
So 1 plus 1 plus 1, 3 is written as, let me do it here so that you can also visually see this. So this is 3 in decimal number system, right? And how is it written in binary? It is written as 1 1. So you can see that in the sum we retain 1 and the carry will go as 1 as well. Okay, so both the sum and the carry are 1 in this case. Is this clear to everybody?
Yes,
Yes,
ma'am.
ma'am.
Right? Any problem?
No, ma'am.
Right. So what is the next step?
Derivation of Boolean expressions.
Yes. Derivation of Boolean expressions for the variables sum and for the output variables sum and carry. Right. Okay. So what we are going to do is let us draw a Carnot map for sum and a Carnot map for carry. Okay. So we have plotted these ones, right? Where are we getting ones? Let us see in the sum. So in the sum, we are getting a 1 in 1, 2, 4, and 7. These positions. Yes. So I put a 1 in these positions. You can see 1, 4, or 1, 4, 5, and 7. Okay. Is there any grouping possible for sum?
No, ma'am. No, ma'am.
No. So what will I get? I will get sum is equal to, I'll simply write down their corresponding minterms, which are x dash, y dash, z. Yes, x
Yes, ma'am.
dash, y, z dash, or x, y dash, z dash, or x, y, z. Right? Is this clear?
Yes, ma'am.
Right.
Yes, ma'am.
Now, please see what are we doing in the next level. I can see that in the first two terms, x dash is common. Yes?
Yes, ma'am.
Yes,
So
ma'am.
using the distributive law, I take it out, and what do I have in the brackets is y dash z or yz dash. Similarly, from these two terms, I take x common, right? And now, when I observe this expression, what do I see? Please look here closely. If I take a to be equal to x, okay, let us take a is equal to x here. Please see this, a is equal to x, okay, and b is equal to y XOR z. Why? Because what is this? You remember?
Yes, ma'am.
Y XOR Z.
XOR
Yes, this is y XOR
Z.
Z.
z. Yes. So what do I have now is, please see, when I assume that this is A and this is B. Okay. So what will I have? Please see here. So what I'll have here is A dash B, right?
Yes, ma'am.
Or this or, right? A B dash. What is this? Isn't this Y X nor Z?
Yes,
Yes,
ma'am.
ma'am.
Yes or no?
Yes, ma'am.
Yes, ma'am.
Right. So what does this become? This becomes A dash B or AB dash, right? And what is this equal to? This is equal to A XOR B. Am I wrong? Am I right or wrong?
Ma'am, right.
This is equal to A. I don't have the symbol of XOR here, so I'm just typing XOR B. Okay. Now let us put back their values. What is X? What is the value of X? It is, what is the value of A? It is A, right? XORed with B. And what is the value of B?
Y
Y.
XOR Z.
Y XOR. Yes or no?
Yes, ma'am.
Yes, ma'am.
So that is how you get this expression x XOR y XOR z. So sum of a full adder is equal to x XOR y XOR z. Any problem? Any problem, students?
No, ma'am.
No, ma'am.
Good. But you will have to work it out with your hand so that you remember. Okay. Now let us derive the expression for carry next, right? So the carry was 1 at the positions 3, 5, 6, and 7, right?
Yes, ma'am.
So let me just plot this in the K map. This is what I get. So this is 3, 5, 6, and 7, right? So what groupings am I able to form? First is this doublet and the other one is this doublet. Is there any quad that I can form first of all?
No,
No,
ma'am.
ma'am.
Right. So when I form this doublet, I'm left with these two ones. So I form this doublet as well. Then I'm just left with this one. So I'll form another doublet, which is this, right? So I'll get 3 terms corresponding to this. What will those be? For this doublet, it will be xy. Oh, sorry, yz,
Yes, ma'am.
Yes, ma'am.
right? For this doublet, it will be xz,
Yes,
x,
ma'am.
and z, right? And for this doublet, it will be x
XY.
and y. Okay, so what have we got? Xy or yz or zx.
XZ.
Zx is the same as xz, right? Because the AND operation is commutative. So is this clear?
Yes, ma'am.
What is the next step now?
Making circuit and verifying.
Yes, making the circuit diagram and verifying it, right? So you can see that I have taken 3 inputs x, y, z, and x and y are first XORed to give me what? To give me x XOR y here, x XOR y. Whenever you draw this on a paper, you should write it down like this. Okay. At each output, you should write down like this. Okay. So now this is XORed with z to give me what? To give me x XOR y XOR z. Any problem?
No, ma'am.
Okay. And this is the sum. So this gives me the sum. For carry, I'll borrow x and z, right? Then x and y. Okay. Uh, and yz is missing here. Okay. Yz is missing here. So that also you must draw. Let me see if I have a tool here. So this is y. I'm drawing this here. Let's see if there is a line tool here. So y and z. So this is z. I'm going to borrow it from here.
Ma'am.
I'm borrowing z from here, okay? And then we will AND them, okay? So that I get a yz.
Excuse me, ma'am.
Yes,
Ma'am, in the first AND gate, it
yes,
has ANDed X XOR Y with Z.
yes, that is also a problem, yes. It should not be this, okay? It should have been x taken from here. Yes, it should have been x taken from here. I think leave this figure. I think we should leave this figure, and I'll just show you the figure from another source. Give me a minute, please. Okay, are you able to see my screen?
No, ma'am.
No, ma'am.
No.
Okay. Is it visible now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right. So this what you see here is the same expression that we have just derived. So this is the circuit diagram for the full adder. So you can see here, instead of Z they put in carry in, and instead of C they are using carry out, as I explained to you. X, Y, they've taken a 3 input XOR gate and they are XORing them together. So this is equivalent to this notation that we just saw. We can take a 2 input XOR gate and do it in 2 steps, or take a 3 input XOR gate and XOR them all together. And then the respective inputs X, Y, right? Uh, this Y, Z, and X, Z are being taken. This Z, this is Z. So they are being taken and fed to these AND gates. So we get X, Y, X, Y, Z, and ZX. And then all these three are odd together to give us a carry out of the full adder. Is this clear?
Yes, ma'am.
Is this clear to everybody, Vita?
Yes, ma'am.
Okay, good. So uh, we are going to be looking at the half subtractor and the full subtractor in the next class. Okay, I'm just going to be introducing one thing to you, one term to you, which is analysis of a combinational circuit. What does it mean? So analysis of a combinational circuit is the reverse of the design process. Okay, so what do we do here is we start with the circuit diagram of a particular combinational circuit, and the goal is to get its corresponding Boolean expression from which it was constructed. Okay, so how do we do this? I'll show you an example for this. Yeah. So sometimes you get a small question, 1 mark, 2 mark question of this sort, that you given a circuit diagram and you're required to deduce a Boolean expression. So this procedure is formally known as the analysis of a circuit diagram. And how do we do it? It is very easy. Please see. So what is going to be this? What are we going to see? We are going to find out the output at each stage and finally arrive at the output at the final stage. And what we'll get is, we from each gate we will keep on getting the terms which we will finally either or and or XOR together in the final gate. Okay, so let us just give a minute and read the steps, although they are not very complicated. It's just what I've told you, but let us just, for the sake of completeness, go through them. Yeah. So analysis of the combinational circuit. So the objective of analyzing a combinational circuit is to either deduce its function or to verify its working. The analysis process starts with a logic circuit diagram and culminates in the production or verification of its corresponding Boolean expression or truth table. Okay, so sometimes you may be asked to construct the truth table. You are given a circuit diagram, and what you will be required to do is construct a truth table. Okay. The goal of analyzing a combinational circuit can thus be seen as just the opposite of the design process. Following steps are generally involved in the analysis process. Step 1. Label the input of the logic gates by meaningful unique symbols. Clearly, at the onset, only the external inputs can be labeled. Step 2. Deduce the outputs of each logic gate for which inputs were labeled in step 1. Assign a meaningful unique label to the outputs. These labels may serve as the inputs to other gates. Right. Step 3. Repeat step 2 till the external, that is the final output of the combinational circuit, is obtained. The external output denotes the Boolean expression corresponding to the logic circuit being analyzed. Step 4. The truth tables can then be drawn corresponding to the Boolean expression obtained in the step 3 if required. Is this clear? Let us just look at an example for this. Okay. So, oh God. Yeah. So this is the circuit diagram which is given to us. So the first step is that we've labeled our inputs. In this case, since no goal statement is given, so some ABC we've taken. Okay. And what is this? What is this gate, students? This is a NAND gate, right?
Yes,
Yes,
ma'am.
ma'am.
Yes,
Yes,
ma'am.
ma'am.
So what is the output that I get at this stage is A and B ka
B
complement.
prime.
Prime.
So this is A NANDed with B, A NAND B, right? And what is this?
Nor
Nor.
gate.
Nor.
Nor
NOR.
gate.
This is NOR. So what I get is
A nod
A
with.
A nod with B.
A NORed with B, right? So this is the first step. This is the first step. This is the second step. And this is the third step. That is the final expression. Okay. So what is this? This is the AND gate. So it is ANDing three inputs, this, this, and the external input C. Okay. So accordingly, you can see that we are ANDing this first input with the second input with the third external input. So this is my final answer. Okay. Is there any problem?
No, ma'am.
Okay. Right. So I'll just circulate the attendance, students. I request you to mark the attendance. How many of you do not have a